as Dakota's introduction showed, I am I'm a theoretical physicist who works on trying to understand the theory of quantum systems, and I've worked on it for many years. And so I realized that probably a large proportion of the room of people in this virtual room don't know much about quantum physics and haven't studied it for years. So for me, I'm going to try and make a big effort today to not uh, to not use expert terminology, which is hard to understand, but I will probably fail. So please, if something's not clear, please interrupt me. And I have a bunch of slides on a bunch of topics. So if we end up having a discussion and I don't get to the end, that's not a big problem. So I think we said we'd go about 40 minutes or so, and then I'll skip to some conclusions. And so I guess now, having said all of that, now I can go to the title of the talk, and it's about thinking about the energy footprint of a technology that doesn't exist. So we're thinking about quantum technologies, which basically do not exist. In terms of technologies, they exist in terms of prototypes in labs, which show some promise, and it depends on the exact technology, how far they are away from actually being able to do what we hope they will do. I know more about quantum computing than other kinds of quantum technologies, so that's what I will talk about today. And so then that raises the question of, does it even make sense to think about the energy or the environmental footprint of a technology that does not exist? So I will hope to try and convince you that it does make sense. So let's skip to my summary. So why try to minimize the energy consumption of something when it doesn't exist, as I said? And also then who should try? And I think one of the points I will make, which I think is quite obvious when you see how complicated a future quantum computer would be, that it has to be an interdisciplinary exercise with scientists and engineers working together. And then what I will give an example of the sorts of things that can be done, taking an example of some work we did in our group, which was one of the papers that Dakota mentioned, where we're not interdisciplinary or not interdisciplinary enough. We've taken a bit of information from each of the communities without being experts in it. So that means our results are certainly wrong, but it's a sort of proof of principle that you can do something interdisciplinary if you bring information, the correct information from each of the things, from each of the technologies you need to build a quantum computer. But I thought, as this is a talk for people who don't know about quantum physics and don't necessarily know about quantum computers, to set the scene first and to say what is a quantum computer, giving some rather weird analogies. I will say the first thing for a quantum computer is you should not think of a computer as you know it. Computers as we know them have been extremely reliable for the last, I guess, 50 years, maybe even a bit longer. They've been getting more and more powerful as time goes on, but they basically never make errors. Even from in the 1970s, they weren't as powerful as they are now, but they basically never made an error. That was the beautiful thing about a digital computer, is it will do any calculation that it's capable of doing without making errors. And quantum computers are very, very different from that. Maybe in the more distant future, they will be a bit more like that, but right now we're a long, long way from that. So the analogy I make is that instead of thinking about a computer, think about a bunch of adults trying to have a serious discussion in the middle of a children's play area. So a completely different thing. And the thing is, the children are running around making a lot of noise. They're giving the adults headaches. So they're forgetting what they're saying. They can't hear each other. And this I think, is a more natural model for what quantum computers are right now and what they will be in the foreseeable future. So the adults here are the qubits, which are the quantum systems that are processing the information like bits do in a normal computer. But the problem is that in the quantum world, everything is quantum. So you have these quantum systems that we can control very well, and we can make them do exactly what we want to do some very complicated calculation. But they're surrounded by other quantum systems that we don't control at all, which are making a lot of noise. And these are the children running around. So you have to do something to control the noise so that the computer can actually do what it's supposed to do, and that the adults can have their conversation. And so then this is all about using resources to fight against noise. And so some of the things you do when you build a quantum computer to minimize the noise, to make sure that the qubits are not too perturbed by all of the things that are happening around them. So some of those things you introduce when you build the computer. So it's about how you build the computer, what sort of you can think of it as putting shielding around the qubits that are doing the work. But some of them, but I would say nearly all of them, require putting in resources all the time while the computer is running to fight against the noise. And most of those resources are electricity in some form or another. So the main things you can do to fight against the noise is to cool down the whole system, which is the adults and the children. And this cooling them down, so putting them at very, very low temperatures, much lower temperature than the temperature of outer space typically, that makes the children less noisy, and then it's a bit easier for the adults to talk to each other. The other big way you can try and solve the problem of the noise is you have the adults get together in groups, and each group they try and do the same thing at the same time. So they shout the same information to another group of adults, and by effect of mass, they overcome the noise that's being generated by all of the children. And that is a very, very simple analogy to what's called quantum error correction, which is the way that you put the qubits that you do control into groups, and they contain multiple copies of the one piece of information in the calculation. So one number in the calculation in the middle of the calculation. And then if one of them forgets the information, or one of them transmitting the information, the person at the other end, the other qubit doesn't catch the information correctly because there's too much noise, then others will compensate for it, and the information and the calculation will advance. So that's the other way to put in resources. But of course, all of that means that you replace one adult by a group of adults for each bit of information that you want to send. So this is my rather weird analogy to how a quantum computer works without actually talking about quantum physics at all, because it's fundamentally a machine in which noise is the biggest problem. And that's very different from our normal computers. So I think, I had one other thing I wanted to say here, but it slipped my mind, so I will carry on. We can think of it as a machine with imperfections and noise, and you have to put in energy and also materials, and you want some target performance. So unlike a normal computer, which always gives you the right answer, a quantum computer typically always has a probability of giving you the right answer, so which is never 100%. So often, depending on what calculation you're trying to do, often maybe 90% chance of giving the right answer is enough. So you might run the computer a few times, and if you see 90, it gives the same answer multiple times, you can be pretty sure that's the right answer. But it's very different from your normal computer where you can do it as often, you always get the same answer. So you always have to fight against this noise. You always have this probabilistic nature, and the typical target performance you want is to say, what is an acceptable level of error? You know the errors will never be zero, but you want to get to an acceptable level. And to do that, you need to inject an amount of energy and materials, and typically the better the performance you want, the more energy you have to put in. So then science is about understanding the relationship between the noise, the performance, and the resources. I would say technology is about increasing the performance and reducing the resources. And then society then comes in with saying, well, what applications are worth given resources? So I haven't talked at all about what quantum computers can do yet. Oh, that was the thing I wanted to say on the previous slide. So we're not quite sure yet what a quantum computer could do. We have these beautiful mathematical theorems which suggest that they can do certain things vastly better than traditional computers. But it's in the case, so if I come back to this picture, most of the theorems say that they can do it better than any traditional computer in the case where the children are not here in this picture, where all of the adults can communicate with each other perfectly. And then some very clever mathematicians have proven very clever theorems that say that it can solve certain problems exponentially faster than a normal computer. But when the children are here and the noise is here and the imperfections are here, it's much less clear. There are some positive signs from the theoretical community saying that it should be possible, but on the practical side, we're still struggling to make things work well. So we're building tiny computers, a few hundred bits, for example, which compared with a typical I think even in your phone probably has 10 to the power of 15, so 10 with 15 zeros after it, transistors in it, so more or less that number of bits of information. And here we're trying to build one with 100 bits of information, so it's definitely not the same scale. And it's not completely clear. There's many, many problems that we know the quantum computer won't be better than a traditional computer at solving. So they're quite niche problems, but some of them we believe are very important for society, optimization problems and things like that. And so I wasn't planning to talk more about the applications here in this talk, except to say that, of course, society has to decide if the quantum computer is expensive in terms of energy, which is one potential future, is that they will be very expensive in terms of energy or in terms of money. Somehow society has to decide if it's worth that. And you might say, for example, if some of the applications turn out that they help us develop better medication to treat cancer, maybe society would say, yeah, it's fine that it consumes a lot of energy. But if, on the other hand, it's if the applications are to, I don't know, choose better ways to advertise to you, particularly based on your particular interests, so that advertising companies can send adverts targeted exactly to you, maybe society would say that is not a priority if it costs a huge amount of energy. And when I say a huge amount of energy, it could be, we still don't know if it will be at the level of the power of a nuclear power station, or if it will be at the level of the power of a similar power consumption to a few electric cars, or somewhere between the two. So that's, and of course, if the power consumption is that of a nuclear power station, what society thinks is acceptable will be completely different from if it's the power consumption of a few cars. So where are we now with quantum computing? Well, so this is to say maybe a little bit what I just said, but in a different way. So here's another weird analogy, is an analogy with flight. So classical traditional computers, like we all have in our phones and you're all probably looking at now when you're listening to me, have been around for a long time. They've gone through various revolutions in terms of the technology. Now we're in the ones that are based on transistors, which have been going since about the 1960s. Before that, they were based on other technologies, vacuum tubes, and before that, mechanical devices that rotated. So we're in the very beginning of quantum computing, so we can expect probably that the technology on which it's based will also change in the future. But if we just compare directly what a traditional computer can do with what a quantum computer can do, it's right now, it's a bit like comparing an aeroplane with a paper aeroplane. Okay, just almost nothing that a quantum computer can do that a traditional computer can't do better. But if we look at how things are changing over time, the situation is a little bit less clear. So if you look, for example, at passenger aircraft, so I don't know, the 747 was designed in the 1950s and built in the 1960s, I think. And it looks pretty much like the modern passenger aircraft that were designed and built in the last 10 years, even though it's a 50-year-old technology. So an expert would say there's many, many differences, but as a non-expert, you look at the difference between aeroplanes that were designed 50 years ago and aeroplanes that are designed now, and it's pretty hard for us as non-experts to see the difference. Of course, if you go back 50 years before that, then there were huge changes, right? An aeroplane from 50 years from 1910 looks completely different from an aeroplane from the 1960s. But so somehow the technology for flight has grew very quickly in the first half of the 20th century, and then at least from a non-expert point of view, looked quite static since then. Quantum computers, let's say if we keep the analogy with the paper aeroplane, then 10 years ago, we didn't even have any paper to make the paper aeroplanes out of. And 20 years ago, we didn't necessarily even have any wood to make the paper out of it. So now, let's say the basic ideas of having a single quantum system that you can control well in a laboratory setting, which is what is the basis for a qubit, was probably at the end of the 20th century. The idea of actually coupling them together and being able to do gate operations like in a normal computer, doing logical operations, which is the basis of all calculations that you're going to do, was probably actually in terms of actually making it work in an experiment, was probably about 15 years ago. And now we're at the stage of, depending on the technology, somewhere between 100 and 1,000 qubits, but with quite bad quality, meaning that for every logical operation you try and do, typically or let's say for every 200 or so logical operations you do, there will be one error. And that's really bad, because even if you want to do a very simple calculation like add the number 5 and the number 8, typically the number of logical operations you need to do, remember it's in binary, so you have some number of logical operations you have to do, is probably tens or maybe a bit less than 100 operations. So even if you want to just add two simple numbers like 5 and 8, this tells you that you are, well, okay, so if you want a slightly bigger calculation than that, maybe you want to add 5 and 25, probably you can be sure that there will be one chance in 2 that it will give you the wrong answer. So that's where we are right now. And of course, the things are advancing very fast. So then there's the question of the future, what will happen in the future. And so if we can believe if we can get over the barrier of controlling these systems and believe what the clever mathematicians tell us, then we move towards a sort of Star Trek world in the future for quantum computers, where they can do things that are just unimaginable now. Now they're unimaginable, but often we believe in solving very specific problems. But some of those problems we believe will be extremely important for society. So they won't change how you probably won't change how you use your telephone or how you do your word processing or whatever, but they will change certain things at the level of society, of optimizing how transport happens, of making better simulations of molecules to develop better drugs. Those are the two sorts of big classes of things that we can imagine. So that's my summary of quantum computing for people who don't know anything about of where we are with quantum computing right now as a technology, rather than all of the fundamental equations and all of the fundamental mathematics that is needed. So then I want to make maybe two arguments for why we should care about energy efficiency of these systems from now. And the first is that I think any new technology now, we understand, given the constraints of the planet are finite, we really understand now that any new technology should be energy efficient from the beginning. I think you can see with things like Bitcoin that it definitely was not designed with energy efficiency as a requirement. And then, of course, you can be in favor of Bitcoin or against Bitcoin. Personally, I'm against it, but we can see that it has taken off in society, and it has now become so valuable that it's extremely hard to replace it with one that consumes less energy to do the calculations that are necessary to make the Bitcoin work. And there are plenty of other cryptocurrencies which are supposed to be more energy efficient, but now it's hard to replace it. So it's good to think about energy efficiency before the technology becomes a real technology, right? So right from the stage of prototyping. And in this case, we need to think about a lot of fundamental research as well as applied research. And of course, there are arguments of an environmental nature for this, and there are also arguments of an economic nature for this. We know that technology is also very expensive. Many of the applications of quantum computing are things that will be useful for governments, maybe more than for individuals or for companies, also maybe for large companies. But that means that it will have to be national budgets that will have to pay for it. And so when governments are trying to reduce their national budgets for various reasons, or to spend money on the ecological transformation, then money is maybe scarce for these other high technologies. So typically, we believe right now that energy efficiency and price are more or less similar. So if you make something more energy efficient, it will also cost less. That may change in the future, but that's at the stage we are in understanding quantum computing. Most people seem to think that that's true. And then, of course, the risks are that, so the first risk based on either of these is that society simply rejects the technologies. So the scientists and the engineers work really well, and they produce a technology that works, but society doesn't want it because it's just too expensive in terms of energy or in terms of money. And the other risk is, so that's the pessimistic risk for people who are developing quantum technology, which is they do the work and no one wants to use it. The other risk is that the technology becomes ubiquitous, and this is what I mentioned about Bitcoin. So now Bitcoin is not used. Probably most of us don't use Bitcoin, but there are enough people in the world using Bitcoin that people are building huge computer servers to calculate all of the calculations you have to do this blockchain thing, which I don't understand, to produce more Bitcoins. So people are running absolutely huge energy budgets and consuming huge amounts of electricity. And I've forgotten the percentage, but it's a significant percentage, I think, of the world energy consumption for calculating in general, for computer calculations in general, right now is people calculating Bitcoin. So the risk is, if a technology becomes ubiquitous, then it could be too late to make it energy efficient, or it becomes more challenging to make it energy efficient than if you did it from the beginning. So those are the general arguments, I think, for any technology. But I wonder if there isn't also an argument. So this is now a very personal opinion, but it's slightly more technical, a specific argument for quantum computing. And my suspicion is that if quantum computing is to become useful, then the usual argument people make or have made in the past is that it can do calculations much, much faster than a traditional computer. But I'm not sure that that gives many applications where speed is really critical. And I think it could be much better. There will be many more useful cases if it can do calculations in a more energy efficient way than a traditional computer. So I think it's a bit early to say. This is my current opinion. I'm not sure if my colleagues would agree with me, and I'm also not sure I will still hold this opinion again in a year or so. Who knows? But basically, the argument is as follows: if in the distant future, if quantum computers are exponentially faster or exponentially more powerful than traditional computers, there won't really be an argument. There will be things that you just can't do on a traditional computer that you can do on a quantum computer. So then, even if it requires a nuclear power station, if society judges that that thing is so important, I don't know, maybe it's because it's important to solve a problem of cancer or something like that, or develop some medication against whatever the next epidemic will be. Then society might say it's fine. We put a nuclear power station, we put a quantum computer next to it. There's no other way to solve this problem. Then in some sense, the comparison with traditional computers is irrelevant. Of course, you still want it to be energy efficient, because if you can do the same thing with just half a nuclear power station, then it's better than if it takes a whole nuclear power station. But it may be but in the nearer term, when, let's say, a quantum computer, so I picked a number at random, but let's say a quantum computer is 20 times faster than a traditional computer. Then if you want to solve a problem, you basically have two options. You can either use a quantum computer or you can use 20 traditional classical computers. Okay, so if it's only 20 times faster, and then you sort of think, okay, but I could just buy a bigger cluster of traditional computers and I could do the same thing. And then, of course, well, how do you decide which of the two you would do? Well, there are various questions. So one question is the calculation time critical? Because if you run 20 traditional computers, you still won't get the answer 20 times faster. You'll be able to do 20 calculations in parallel. So if the answer is time critical, and certain things you might need to, if you want to, I don't know, optimize traffic on auto routes in real time, maybe if the calculation takes 1 day to give you the answer, then that doesn't help you because the traffic jam has already happened and gone past. On the other hand, if it's 20 times less, so maybe 1 hour to do the calculation, then that might be enough to say there's a traffic jam and to solve the problem of making all the cars get out of the traffic jam in an intelligent way. So that's the sort of optimization problem people claim quantum computers might be good at. There will be some applications where it is time. The answer is time critical, but often it's not. You know, it's if you want to simulate some chemical interaction to try and develop a new drug, if the calculation takes 1 hour or 20 hours, maybe doesn't make such a big difference. But if the calculation is going to be repeated many, many times, or if it's parallelizable, then actually there's not a big advantage of using the quantum computer over having 20 traditional computers. So in that case, if speed is not very relevant, what is the relevant parameter? Well, maybe it is energy consumption. So if you have a choice between a quantum computer and 20 traditional computers, I guess in the real world, price will also play a role. But if we're thinking from the good of society, then maybe the most important thing is which which one consumes less energy. If you can do the same calculation on 20 traditional computers or on one quantum computer, which one uses less energy per calculation. So my claim based on this is that maybe speed of quantum computers is not going to be their final useful use, but actually, hopefully, if we can build them and make them energy efficient, then it will actually be the fact that they use less energy per calculation that will be really helpful. So do we think the quantum technologies, and particularly quantum computers, will be energy hog, or will they have an energy advantage? We don't know yet. We need to develop new methodologies to answer these questions. So that's the job of scientists and engineers. We need objective figures of merit. So we need objective ways to compare a traditional computer with a quantum computer, or between two different kinds of quantum computers built with very different technologies. We need to find a way to compare them. And so for that, we also need to build an interdisciplinary community and develop common languages and tools between engineers of different kinds, and physicists and so on. Okay, I think I can probably. So, okay, so the thing I want to show here is that there is what's called the full stack of technology. So it's a system level view of a technology, and this is one for a quantum computer. So you have somewhere in the middle, you actually have your quantum computer that's doing the calculation. But for it to work, you have to have a lot of electronics around it, traditional electronics around it to control the qubits. You need to have a lot of what's called enabling technologies, which is typically cryogenics to keep the qubits cold, which are big refrigerators. So it's technology based on refrigeration and pumps. It uses liquid helium and things like that, but it's very similar to the refrigerator in your kitchen, which has a pump and pipes that moves the cold around and so on. So that's at the bottom of the stack. You have all of these technologies that are not quantum, but you need to make the quantum parts work. Then you actually have the qubits that are doing their job, but then on top of that, you have all of the things that go up to the end user. So you have some sort of architecture in a software sense. You have compilers, just like you do to run programs on your own computer. Then you also need some algorithms. You need to say, what is the logical procedure that you use to solve a problem that's interesting to you? And then you need the top of the stack, some sort of interface for the end user so that they can tell the computer what they want it to do, and they can understand the answer that the quantum computer gives. And what we notice in the examples we've studied is that there are weird connections between all of these things. So you can, it's hard to know how to optimize your quantum processor if you don't know certain information about the enabling technologies, about the cryogenics to keep the qubits cold, for example, that there can be weird connections between the algorithm you want to run and, for example, and the temperature of your qubits and things like that. So I might show one example of that a bit later on. So you do need communities who work as experts on each of these layers, but you also need a community of people who are capable of seeing the whole picture and moving with ease between the layers and getting the information they want from the experts in each of these layers to get an overall picture of what's happening. And I think also it's the question of looking at the energy consumption is all about doing less with more, doing more with less. And so a byproduct of that is often it's a nice subject, I think, or I try and encourage people that it's a nice subject where small teams with less equipment can really make a contribution. Right now, IBM has just made a lot of news yesterday or the day before, publishing a paper and they probably invested of getting some wonderful new results in quantum computing. But they had, I think there are 200 authors on the paper, and they probably invested millions in that. So if you're a small research team doing with 3 or 4 people doing with a small budget, then you can't compete with that. But what you can do is you can figure out smart ways to do more things with less. So to improve the efficiency of one small part of the quantum computer, knowing that it will have an impact on the overall quantum computer, and maybe your technology that you develop and the ideas you develop will be used later on in the next generation of quantum computers developed by IBM or by big research institutions. So then we come to some questions that are for social scientists and citizens, which is definitely outside of my area of expertise. But so how do we judge when something is worth the resources or the environmental cost? So when so as scientists, we can tell you what are the costs and what are the benefits of a quantum computer, but somehow it has to be up to citizens and society in general to decide if the benefits are worth the costs. And one particular thing that is a challenge right now in quantum technologies is most of us come from a background of pure science, which was open knowledge. We would happily share our knowledge with everyone. And now more and more the people who are funding the research are saying, no, there's a security argument. We don't want certain governments or certain companies to get hold of whatever you're developing. And so they're trying to put barriers around. So somehow society and citizens should be having a say on things like that. And of course, there are questions about if the technologies are developed, will they have negative uses? Probably. Most technologies have negative and positive uses. So how do we develop methods legal or voluntary methods to avoid the negative and emphasize the positive? And of course, then there are so these are the things that as a scientist, we don't have any answers to these questions, but at least we've thought of these questions. But certainly there are other questions that as scientists who work on quantum systems, we haven't thought of. So our blind spots where someone, I don't know, who's an expert in, I don't know, accounting might say, okay, but in my domain of accounting, there's this problem, and that we, of course, as quantum scientists, we don't know anything about that. So it's important to have this interaction with society and with experts in all domains. And the question is then who should decide about all of these things? I don't think it should be the scientists, the engineers who decide about any of these things. We can provide the information. We can try and do our best to make predictions that are reliable. And if we leave things as they are, then maybe it will be market economics that decides, or should it be somehow our institutions that decide, military, universities, governments, whatever, depending. And of course, that depends which ones will decide, depends on a lot on what the applications turn out to be. So that's a bunch of questions. So that's I guess, the non-technical part of my talk. So I guess I have about 10 minutes left, so I might launch into a few slightly more technical things. So this is work, and then come back at the end to the more general point. But I guess I've made all of the general points so far. So this is a work we did with the people. You can see the photo here. So it's quite a small team. It's not 100 people. And we were trying to think about how to come up with a method to minimize the energy consumption of a quantum computer, given how complicated it is. So we think we've come up with a method. We don't necessarily trust the results we have, because I think we have the methodology, but not all of the ingredients we've put in, because there are a lot of ingredients to put in. Not all of them are perfect. So you shouldn't necessarily trust our results, but what we hope is that we have a method that's useful, that can be improved over the coming years. So this is a picture of one type, a simplified picture of one type of quantum computer that is being proposed. So I think it's more or less a good picture of the one that IBM made their announcement about in the news a couple of days ago. So it's one where you have superconducting qubits. So the qubits are down here and they have to be kept very cold. So they're inside a refrigerator, which is this black cylinder shape, represents a refrigerator, and that refrigerator is inside another refrigerator. Okay, so typically the first refrigerator cools things down to about 50 Kelvin, and then actually there's usually multiple refrigerators. Then inside that, there's one that cools things down to about 4 Kelvin. So that starts to get about the temperature of outer space. And then there are ones that cool it down to a few millikelvin. So that is probably between 500, about 500 times colder than outer space. So very, very cold. And then you also have to control these qubits, and you have to read them out. So you need to control them, to tell them what to do, and you need to find out what they've done and to use the information to get the answer to your calculation. So for that, you have to have lots of other electronics and normal computers, and somewhere there's an end user. So the end user interacts with a normal computer, which then has some electronics which generate pulses, probably going down optical fibers to some electronics that then send signals to each of the qubits. And then there's some amplifiers that read out the state of the qubits that go back to the control electronics and finally come back to the end user in a way that they can understand, that gives them useful information. And all of this generates heat, right? We know that your computer heats up, so any control electronics generates heat. The qubits themselves, they're generating heat when they're operating. The amplifiers generate heat, and all of this heat has to be extracted to keep the qubits cold. Otherwise, they would heat up. And so that gives you a cost to all of the things you're doing, a continuous cost, which is the cost of running the refrigerator, just like if you put I don't know, if you manage to put your electric toaster inside your refrigerator and turn on the toaster, then the toaster is generating heat, and your refrigerator, if it's trying to stay cold, try and keep its inside cold, so it's trying to extract all of that heat, and it's using even more electricity to extract that heat. So that's the story we have here. And of course, then there's the whole software level, which is you have the software which is running inside the classical computer that is controlling the quantum algorithm. So that's the protocol of logical operations that you do on the qubits that take you from your input to what you want as your output of your calculation. And there's also a lot of error correction, which is the thing I mentioned about if you spread the information or many copies of the information over many qubits, then if one qubit has an error, it doesn't stop the whole calculation proceeding. And so that is based on quite subtle and complicated error correction protocols. And that means that if you want to have a lot of protection against errors, you need to have a lot of qubits, because you will spread one bit of information will be spread over many qubits, maybe over 100 qubits. So if you want to do a calculation that requires 1,000 bits of information, you could quite easily get up to hundreds of thousands or even millions in some cases of qubits. And each one of those qubits needs some control line to control it, some amplifiers to read it out, and all of these things. So we immediately get up to large structures when Google currently have a computer that has about 100 qubits in it, and predictions are that if you wanted to do really revolutionary things that no traditional computer could ever do, you probably need millions of qubits. Although that's also disputed about what point, how many qubits you need before you can really start doing things that a traditional computer cannot do. So certain things even at the level of 100 qubits, but most of those things that we have examples of at the moment are not useful. They are tests of showing that the quantum computer can do something that a classical computer cannot, but they're not They're not things that are really useful for society, let's say it that way. They're not things that anyone actually wants to know the answer to. They're not calculating problems that we want to know the answer to. They're more tests of showing that they can do something that a traditional computer can't do. But that's something that's also advancing very fast. So then we developed a methodology that we applied to superconducting qubits. And so here's a list of, so I can probably skip this slide if the experts want to see it, so they can ask me and I will, because it gives a list of references basically for the experts. But you can see we developed the methodology for superconducting qubits, so one kind of technology of qubits, and it's since been applied in various forms to different kinds of qubits and also to quantum communication rather than quantum computing and so on. So we've got so we're happy to see that our method is starting to be used by different groups around the world. But it's the early days, so we will see how it goes on. And so here's an example, and then maybe I will stop. So these are qubits. So this is qubits that are made of spins for the experts in the room. So each electron has a spin, and so they're trapping an electron in a little box and using its spin, which can have a state 0 or 1. It's a two-state system. But of course, it's quantum, so it can also be in a quantum superposition of the two states. And this is a technology that's being developed in various places around the world, but including in Grenoble. So there's a startup, Probly, which is developing this in Grenoble. And one of the things about these spin qubits is they're quite robust, and so they work over quite a large regime of temperatures and of speeds. So speed of the gate operations. So they're much wider range of temperatures than superconducting qubits, which is the ones used by IBM. And so then the question is, well, if you have this wide range of temperatures and of speeds you can operate them at, what is the best speed and best temperature? Well, so this is a map so you can think of this as a landscape. So these are the mountains and this is the valley. So this is a map of the energy cost as a function of temperature and of speed. So we can see that the energy cost gets very high when you go very fast. That's quite similar to a traditional computer. Traditional computers, when the clock speed goes up, typically their power consumption also goes up and they start to overheat and all of these things. What's weird about these quantum computers is that if you go too slowly, you also have a high energy cost because there's a lot of static costs. You need to keep the qubits cold. So if you need to keep them cold for 1 hour, it costs more electricity than if you only need to keep them cold for 1 minute, right? So that's why the energy cost at low speed is high. And then somewhere in the middle, and then as you want to get them colder and colder, they cost more. It costs more and more energy as well. So at the bottom, it's high energy cost. So then somewhere in the middle, you have a low energy cost regime when they're not too fast, but also not too slow, and when they're not cold. So that's the lowest energy cost. But now the idea of our methodology is that it doesn't make sense just to look at that because that's just the costs. You need to compare with the benefits. So the benefits, so now we start to get a bit more complicated. The benefits are some other set of lines in this space or based on the quality that you need. So the higher the quality you need, the more you go onto these blue lines that are in the region of high energy cost. So a given quality is the same anywhere on this blue line. So it's a bit like you're walking in the mountains along this path because that's what you need in terms of quality. Let's say you want medium quality. So I haven't defined what medium quality is, but a certain probability of having errors in your calculation. So you're walking along here, you're at the top of the mountain, then you walk down the mountain, and then you're stuck you're in the valley. But then if you continue, you start leaving the valley again, and you start going back up the mountain. Okay, so it's obvious that For this quality, if you just want to minimize the energy cost, you want to be somewhere here. This is the lowest place on this path. This is the point on this path, which is the lowest into the valley. If you want to do the calculation as fast as possible, you want to be over here because that's high speed. But low energy or the minimum energy cost is not the highest speed. It's somewhere in the middle, but it's also not low speed either. So that's very different from a traditional computer. Traditional computer, the slower you work, the less it will cost. So you can plot these lines and then you can explore. So then if you write down all of the equations for all of this and you model it on a computer, you can find the optimum speed and optimum temperature for a particular quality of calculations. And of course, this is a cartoon. If you want to see what a real plot looks like from our simulation. So this is one, we're not 100% sure this one is actually right because it's work in progress and we need to do a little bit more debugging on the code. But you see, so the white lines in the cartoon are the same as the white lines in the plot. You see there's lots of steps coming from the fact that the cryogenics have multiple temperature stages. And the blue lines here are the blue lines or in this plot. But the color scale is different. So here, yellow is the most expensive and blue is the cheapest energy cost. So you see it's this picture, the cartoon already looks complicated, but the reality is even more complicated. You need to do a simulation on a computer to catch all of the details. So then I think I can skip that example. So we have other examples about error correction. Which I will skip over. So basically the point is that there are two ways to deal with errors. One is to, so let me, well, no, I think you shouldn't look at the transparency, but it's too complicated. But there's two ways to deal with errors. One is to reduce the errors by reducing the noise by making the qubits very cold. That has a certain energy cost because the colder you make the qubits, the more expensive it is. The other is to do more error correction. So to reduce the noise, leave the noise the same, but to group the qubits together into groups where they share the same information and overcome and reduce the chance of errors in the calculation by doing that. But of course, that means you replace, as you do group them into larger and larger groups, you need more and more qubits. So that also has an energy cost. And so what we did in this work was we tried to look at the compromise between the two. So you can, in what conditions is it better to make the qubits colder and to reduce the noise? And in what conditions is it better to leave the noise as it is and to do more error correction? And it's complicated. I guess that's the main message of these ugly plots is that it's complicated and it depends on a lot of details. So if you want to minimize the energy consumption, you need to understand those details and on a more or less on a case-by-case basis, figure out what is the right amount of error correction and the right temperature for your calculation. So I maybe skip, well, okay, so and in that work, we then looked at different scenarios for one particular application, which is maybe not the most interesting application, but it's cracking RSA encryption, which is the encryption that you use when you have your, I believe it's the one you have when you look at HTTPS, you know, with a little padlock on your browser, then you're using that kind of encryption. And of course, when you communicate with your bank or whatever, you're very happy to use that kind of encryption so people don't get your passwords and your bank details. So one of the applications of quantum computers could be to break that kind of encryption, which is bad if they use it to get our bank details, but good if they use it to listen to messages from terrorists or whatever. So it's like most technologies has good and bad things. But the point here is that so the number of qubits you need depending on the quality of the qubits that you have. So if you have existing quality of qubits, then you can't do much. But if you make them better, then you can start to use a quantum computer in principle to crack these codes. But it will take billions of qubits. And as you increase the quality, the number of qubits you need, because you need less error correction, the number of qubits goes down, but it's still billions. It cracks the codes quite fast, but it would require a huge power consumption just because there are so many qubits. So we're talking about nuclear power plants, or in the best case, power consumption similar to the biggest supercomputers in the world. But on the other hand, if you use a more efficient method of doing the error correction, so this is using an old-fashioned version of doing the error correction, if you use a more efficient one, then it's not what we claim is it's not impossible that you could get down to power consumptions of that of an electric car. There's a huge amount of progress, technological progress you'd need to do to get there, but we don't believe it's against the laws of physics to get down to such low power consumptions for that sort of thing. And that means would be, if we could do that, vastly less expensive than doing the same sort of thing on a traditional computer. So maybe I stop there and go to the conclusions. So why try to minimize the energy footprint of a technology that doesn't exist? Well, I tried to convince you that, the main message I want to say is that we should try and do it. We know our predictions will be wrong, but we hope the methods we develop will be useful. And in the short term, we can hope that our predictions will be good enough that they will help designers do more with less. So when they're making the next generation of prototypes of quantum computers, people always want to squeeze a few more qubits into their existing system. So maybe the methods we're talking about can help do that, because often the limit is energy consumption, overheating, things like that, which are directly related to energy consumption. And in the long term, if the technology works, then we want to make it as green as possible. And for that, we need interdisciplinarity between scientists and engineers. And then we need a broader community that decides what application is worth a given energy footprint. And so with that, I will stop.
Thank you so much, Rob.